Recording. Okay. Yeah, welcome everyone to the next seminar. So I'm delighted to have Nick Rod with us again for the second appearance in this seminar series. So many people here today will know Nick very well. Nick is currently a divisional fellow at Lawrence Berkeley National Laboratory in California. And well, many people will know Nick's work on various aspects of dark matter, and that's basically what we're going to hear about today. Specifically, some quite interesting new work on a quantum description of wave dark matter. So thanks very much, Nick, for taking the time to speak to us, and I'll leave it with you. Thanks.
Thanks, Kieran. No, it's my great pleasure to have the opportunity to speak here. And thanks to all of you for coming along today and giving up your time to hear about what I've been thinking about. So specifically, what I want to use the next 50 minutes or so to tell you about is some recent thinking I've done about something that has really bothered me for a long time in the discussion of wave dark matter. And that relates to how do we think about the distinction between particle dark matter and wave dark matter. So I'm sure you've all heard this before, that if dark matter is very heavy, if it's like a WIMP, then we should have the picture like on the right-hand, top right of the slide here, where we just have a gas of particles flying around to the location of the Earth, and maybe we'll be so lucky as one of them might scatter off some detector that we've built here. However, as the dark matter gets lighter and lighter, people say that eventually the occupation number becomes so large that it should be described as a classical wave, and instead we should therefore be thinking about it very differently. And of course, especially the experimental community has taken this line of thinking very seriously, and they are now pursuing enormous experiments to try and search for these sorts of dark matter waves. But I think as a theory community, the very least we can do to help our experimental colleagues is to think very seriously, do we really understand what we mean by this dark matter wave? Because I think there's a number of heuristics that are often deployed when we're talking about this. And what I want to tell you about today is at least some recent attempts to put on more solid footing the various languages, the general language and ideas we have around wave dark matter. So primarily, this talk is going to be based upon this paper that I had out 2 months ago now with my amazing collaborators, Dongyon and Lian Tao. And while probably many of you are familiar with Lian Tao, I really want to emphasize the amazing work that was done in this project by Dongyon. He is a graduate student at Yonsei University in Korea. He actually came over and worked with me for a long time in CERN on this project. And he's also on the market this year. So if you're hiring, please keep an eye out for his name. He's just absolutely brilliant. So I've already given you the overarching motivation, but maybe let me give you some more specifics about sort of why this program is so exciting and sort of some of the questions that I came into this project with that I was looking forward to resolving. So of course, there's many different ideas for what wave dark matter could be, but really I think the focus of the community is on the search for axion dark matter, and primarily the fact that axions could couple to electromagnetism through this Lagrangian term I'm showing you here, this A coupled to F and its Hodge dual. And one of the fundamental aspects of this is that this Lagrangian term is dimension 5. And so that means that this unknown coupling between axions and electromagnetism has inverse mass dimension, this GA gamma gamma, and that'll be relevant in the next couple of slides. But broadly, the reason that this is our focus is that we think that axions are extremely well motivated, and we're very good at manipulating electromagnetic fields. So if these two things exist, then we have a very good chance of detecting them. So let's think about what the parameter space looks at here. If you want a far more comprehensive view than what I'm going to be telling you about now, you should go and look at Kieran's wonderful GitHub repository on this. But broadly, what I'm showing you is the unknown axion mass on the x-axis. I'm showing you this over 20 orders of magnitude. This is, of course, a symptom of our broader problem that we don't know what the mass of the dark matter could be. And on the y-axis, I'm showing you this unknown coupling between the axion and electromagnetism, which I give units of inverse GeV because recall it has inverse mass dimension. And also, just to say a point I should have mentioned at the outset, of course, feel free if you have any questions throughout to just interrupt me. There's no need to wait till the end. So let me just quickly run through what this parameter space looks like, where we're at and where we're going. And to begin with, at the top end of the parameter space, you don't even need the axion to be dark matter in order to set very strong bounds on it. And also just to say, I think that the bounds I'm showing you are out of date. There are some more up-to-date ones on Kieran's repository. So what is happening for these higher couplings between the axion and electromagnetism is that if the axion just exists in the spectrum of nature, then you should be able to produce these axions in hot compact objects like stars. And then you could, for example, look for anomalous cooling of these objects, or you could even look for the axions directly, which is, of course, what CAST did for many years at CERN. And so because we're so excited about axions, searching for them, even if they aren't dark matter, is an enormous program. My own contribution to this space recently was to contribute these two fingers you can see on the right-hand side of the plot here. But there's a lot of active investigations about how we could improve these searches further and further. If, however, you assume that the axion is dark matter, you can rule out the right-hand part of this parameter space. And the reason for this is that through this same coupling, the axion could decay to 2 photons. And again, because this is a dimension 5 operator, what you'll find is the decay rate has to scale as the mass cubed to make the dimensions work out. And so at high masses, it decays faster and faster and faster. Eventually, it wouldn't be around to make up the dark matter of the universe. But well before then, we can set constraints on it by just looking at regions of large amounts of dark matter. Do we see a line of photons coming out of there? If we don't, we're able to set a constraint on this. And this is where these dark ray constraints come from on the right-hand part of the parameter space. That tells us that if the dark matter of the universe is an axion, it has to live to this lower left parameter space. And so, of course, we can ask our colleagues to search as much of this space as possible, but notice that the axes are logarithmic, so this will be enormously challenging. And so it's helpful to provide them with a theoretical prior about where we best think the axion could live in this parameter space. And one of the reasons people are so excited about axions is that not only could they be the dark matter of our universe, they could also resolve the long-standing strong CP problem. But as you'll be familiar, the strong CP problem is not a statement about electromagnetism, it's a property of QCD. And so in order to solve this, the axion must couple to the QCD sector. However, one can then show that through this coupling to QCD, the axion inherits a mass, and the size of the mass it inherits is proportional to the coupling it has to QCD. The stronger the coupling, the larger the mass. And so what you find is that in these scenarios, the larger the mass of the axion, the stronger the coupling you have. And so you roughly live on this linear yellow curve that I'm showing you here. The reason why this is sort of a band, however, and not just a single line, is that that statement is only rigorously true about the QCD coupling, whereas here I'm showing you the electromagnetic coupling. There's some irreducible connection between the two, for example, through the mixing with the pion, but there can also be some UV, the neutral pion, there can also be some UV dependence on this, and that's why there's this broad band. But basically, this is the region where you would want to target if you want to search for an axion that not only is dark matter, but also solves the the strong CP problem, sorry. So this is how we're doing in terms of searching for these at the moment, or at least when I last collected the up-to-date results on this. It's a very fast-moving field. And this is the domain of these axion haloscopes, which are instruments looking for the axions that make up the dark matter halo of the Milky Way. And you can see if you have a strong prior on the mass of dark matter being around a micro EV, then this is an incredibly exciting time because ADMX is cutting into the most interesting part of the parameter space. They're regularly producing new results, and it could be any day now that they write the paper that discovers the axion and resolves what dark matter is. However, if we stare at the parameter space for a bit longer, we will see that beyond where ADMX is cutting into this, or this sort of microwave cavity regime, it seems that we're not doing very well at getting down to the QCD axion prediction. In particular, if you look at lower masses, you can see that instruments like SHAFT and ABRA are not even getting below the star emission bounds yet, even after invoking this extremely strong assumption that the axion they're looking for is dark matter. But the reason to mention these instruments is because they were just prototype devices to check whether some new types of axion haloscopes operating at lower masses could operate. And I can tell you that they operated essentially exactly as the theorists predicted. Abra, for instance, was very small. It was only about the size of a grapefruit. And the idea then is that in the future, we can build much bigger versions of these instruments and cut down far deeper into this parameter space. And ultimately, hopefully, with an instrument like dark matter radio, in the coming decades, cover this QCD axion band down to masses even below a nano EV. And this is just one of many ideas the community has put forward. There is a huge number of these that are being pursued. And broadly, the hope is that within the coming decades, we'll completely cover this parameter space. And so if you have a strong prior on the axion being the dark matter, and it's certainly something that I believe could be very reasonable, then this is an incredibly exciting time because we could be on the verge of the discovery of dark matter. But I don't think, as I said earlier on, as a theorist, we should just sit back and wait for this to happen. We should think seriously about what's going on, and if we really understand how dark matter behaves in this ultralight wave-like regime. And so before I tell you about the new work, let me just tell you about some of the things that I found puzzling. In particular, I think this field is really full of heuristics and surprises. Often when people just invoke this idea that dark matter behaves like a classical wave, they start to wave their hands a lot and say that eventually you should be able to describe it as something like a cosine. Furthermore, one of the fundamental properties of this dark matter wave is its coherence. And it's often, despite this being a really fundamental property, this coherence is often only given sort of tilde definitions in terms of both its coherence time and its coherence length. And further, there were certain surprises that had come out of the literature. Like, for example, it turns out that wave dark matter observables seem to be far more sensitive to velocity substructure than are their direct detection or WIMP counterparts. So let me just dive into some of these heuristics and surprises.
Sorry, Nick, can I ask a stupid question at this point? Or well, so the coherence only. So of course, there's an issue if you're at the edge of where it's a dark matter particle versus a wave. But if you are really in a wave regime or really in a particle regime, I mean, you can make the limit should be fine in some sense, right? Or whatever the tilde means should be fine.
Good. I guess maybe this answers your question. Please let me know if it doesn't. But maybe to give you the end statement of the talk today, for most of what I'm saying, this will not change the way you should think about wave dark matter by orders of magnitude. Okay.
Yep.
I'm looking to put equal signs on all of these things and correct things that are like factors of 3 or 5 around the place. But broadly,
Correct.
so that's ultimately what we will do. But I think it's also very important to just make sure that everything works and just to confirm that all of the words that people have been using match up. Now, I think there is actually a chance to have even bigger surprises than what I've just mentioned. I'll mention some examples in a slide or two. But broadly, yes, the goal is to put equals everywhere there's a tilde and fill in those gaps, if that makes some
I
sense.
see. Okay. Yeah, absolutely.
Hopefully you'll have a better picture of that at the end. And please let me know again. Thanks for the question.
Yeah, it matters. I mean, I agree with you. It matters when you're looking at something.
Sure, yeah, and the right place to start is tilde, tilde, tilde. But when you're going to spend $100 million on an experiment, I'd like to make sure I can put equals. Yeah, good. Thanks for the question. So let me just quickly go through some of these heuristics and surprises to give you a sense of at least why I cared about this problem. So the first and really the biggest heuristic was this transition I mentioned earlier on between classical waves and a gas of particles. Because I was trained as a particle physicist, as I'm sure many of you in the audience were. And so when we're talking about particles, I have a pretty good idea of how to think about this. I can think about some quantum field theory mode decomposition. And if I'm talking about some scattering experiment, I could imagine starting out with a calculation where the incoming particle is in some momentum eigenstate, for instance. But then when I go to this classical wave picture, this is something that I find far more perplexing. And honestly, here are the sort of questions you could come up with, like where exactly is the transition? What happens near the boundary? Does it just immediately become a wave, or is there some smooth transition region between the two where it behaves differently? And furthermore, why is it, this is something that had bugged me, why is it that large occupation is enough to say that this thing is a classical wave? To say some more about what I mean by this, there are clear counterexamples. So for example, if I take a specific quantum state, and in particular, if I take a Fock state, which is where I just have some number of quanta of my field, no matter how many quanta I put into that Fock state, this thing will never be classical. It's the most quantum thing you can imagine. It's a measure of the quanta of the field. So even in the limit with an enormous number of quanta in a Fock state, that's never going to be well described by a classical wave. So why is it that we can just use the words for axion dark matter that large occupation means classical wave? These are the sorts of things that were bothering me. Furthermore, this coherence, I think, despite being an extremely important ingredient experimentally, as I said, was only ever defined with tildes. Now, I'm sure it was defined earlier on, but one of the first references I'm aware of that gave a tilde definition was this fantastic paper by Peter Graham and Sajid Rajendran over a decade ago now. And they said that the coherence time is roughly 1 over the mass times the velocity squared, and the coherence length is like 1 over the mass times the velocity. So that's very intuitive in some senses as sort of the scales over which these things should vary, but you can ask questions like, what velocity do you mean? Because when you start thinking about the local speed distribution of dark matter, there's many scales that enter. There's the scale at which the Earth is moving around the galactic center, and there's also the scale at which there's a velocity dispersion of the field. So in some more recent work by myself and Josh Foster and collaborators, we tried to understand which of these there was. And so, for example, we said that the coherence length should depend on the velocity dispersion, whereas the coherence time should depend on both of those velocity scales that I just mentioned. But I mean, even then, you can ask, there's still some puzzles associated with this. For example, you can see in our expression for the coherence time, it depends on the speed of the Earth. And so you can ask, what if I took an experiment and I put it out in the solar system? Sorry, I put it out in the halo of the Milky Way, but at rest. So I wasn't moving at the solar velocity. That would make it seem like the coherence time diverged and potentially the axion would be much more detectable. So there were some things like this that were confusing me in the back of my mind. Furthermore, to say, I think as a field, particle physicists didn't really understand coherence very well. And to give an example of this, although there are others, some collaborators and I went back and recomputed what the sensitivity was of Caspar wind, which is an instrument probably many of you have heard of, searching for the axion-nucleon coupling. This is a fantastic idea where you repurpose the amazing sensitivity of NMR devices to look for this axion dark matter wave. But what we found was that the original papers just hadn't understood how to use the coherence time at all. And or at all accurately. And once you included an accurate calculation of this, we actually found that Caspar wind should be even more sensitive to dark matter at higher masses. So this is just to say that I think giving a better sense for how these things are behaving is very important when we're thinking in detail about the detectability of wave dark matter. And the last thing I want to mention is, I mean, I think probably Kieran is well aware of this, but maybe not others, is that something that had puzzled me is it seems that wave dark matter experiments are much more sensitive to the form of the speed distribution of dark matter. And what I mean by this is if you go through a calculation for how sensitive you should be to, say, the axion-photon coupling, you find that you get some integral over the speed distribution of the form I'm showing you here. And in particular, it depends on the speed distribution squared. And just as a reminder, f of v is essentially the probability distribution for what the speed of dark matter should be as measured here on the Earth. You can do the same calculation for what cross-section sensitivity you should have at wind direct detection. And what you find is a very similar looking expression, except instead of f of v squared, you get a linear dependence on the f of v. So, I mean, if you haven't thought about this before, you could ask the question, well, what's the big deal of this? So just to give you an example for what changes here, let's imagine just a very toy case where you have a very narrow dark matter speed distribution, because in truth, this is actually roughly what we have, although this is, of course, idealized. So I'm showing you at the bottom here, imagine we just have a box that describes the local speed distribution. It's centered around some mean velocity v bar, and it's very narrow. And a measure of the narrowness is this Q factor I'm saying here. So the larger Q, the narrower the distribution. But of course, because this is a probability distribution, it better integrate to 1. So if it only has a very narrow support, it has to have a very large value at that point in order to still integrate to 1. So that tells you what the height of this distribution is. And then for this very simple ansatz, you can actually evaluate these integrals straightforwardly. And what you find is that for direct detection, the result you get is independent effectively of how wide the distribution is. Whereas for axion direct detection, you find it is linearly sensitive to the width of this distribution. And so for dark matter, this is a huge enhancement because we expect this sensitivity to be very narrow. So you can ask, why is that happening for wave dark matter? And even though I can tell you this is something that came out of an explicit calculation I did, fundamentally, if you press me, I had no idea why this was coming out. So these are some of the puzzles that were in the back of my mind. I think they go from the very general about how do we even think about this wave to some of the more specific things that came out of detailed calculations. But broadly, I was motivated, given all the effort that we're putting into searching for this, I think there's a strong motivation to go back and make sure we really have a rigorous description of the physics. And so that's what we started to dive into in this paper that we put out recently. And let me just tell you some of the questions that we look to answer, and I'll give you some discussion of today. So the first of these is I want to think seriously about how do we describe this whole dark matter field from a real quantum mechanical base picture? Because if there is a classical wave description, it can only be emergent. The quantum mechanical one must be the fundamental description. So if we're going to talk about a quantum state, ultimately the fundamental description of that is a density matrix. And so I'll tell you some words about how you can describe a density matrix of dark matter. And the second part of the talk, I'll give you some words about how you can give rigorous definitions to these coherence quantities that I described, how to think about them and how to define them with equal signs rather than tildes. And if there's time at the end, I'll show you what you can do with this formalism by demonstrating that you're not required to assume that dark matter is very heavy and therefore behaves like a gas, or particles are very light and behaves like a classical wave. You can really use the full quantum formalism to compute at any mass, and indeed you can actually do calculations right through this wave-particle transition. Good, so with that said, that's the broad motivation. What I want to dive into first is this discussion of a density matrix of dark matter, but let me just pause briefly in case there's any questions about the overall motivation before I dive into the specifics.
I had a question. If you go back to the plot about on the Caspar, and maybe it's just so what's the misuse? Like, what is it? Maybe you mentioned and I didn't understand what.
I did not. No, it's totally fair. I didn't go into this. So basically, the assumption had been that these axion waves come in and they're trying to grow some signal. Like in a cavity experiment, you're trying to deposit power in the cavity, or in the NMR experiment, you're trying to tip the spins over. But you've got some driving force that's either depositing the power or tipping the spins. And what had been assumed in these calculations is that once you hit the coherence time of this driving force, this effect saturates. And there were some words about you're pushing as much as you're pulling, and so everything should shut off. That sounded very convincing, but if you sit down to compute this, it's honestly an undergrad classical mechanics problem. You just solve the simple harmonic oscillator with an incoherent driving force. You find that although the growth of the effect slows once you hit the coherence time of the driving force, it does not stop. It transitions from growing linearly in t to the square root of t. And so this means that actually you can get much more juice out of the system by just running it for longer because the signal continues to grow. So that was the effect that was missed.
I see.
But yeah, it's a bit far afield, but we talk about a lot in this paper that I had with Jeff, Stefania. And
I see. Okay. All right. Cool. Thank you.
No, thanks for the question. Good.
Sorry, Nick, just to go back to that slide again.
Please.
How do you go to higher masses than what the Graham and Rajendran paper a decade ago projected?
Good. Yeah, no, I mean, this maybe is a can of worms flashing this, but thanks for the question. As far as we can tell, and I've chatted, my collaborator chatted with Peter Graham about this. I think they just dropped a factor of 2 in the definition of the Larmor frequency in their original paper on this. So it's literally, at least in the helium case, it's a factor of 2. We think there was some other issue in the xenon case, but the reason we go is we think they just dropped a factor of 2 in the definition of the Larmor frequency. So this was just a minor typo in their calculation. The other one was more conceptual, if that makes sense.
But xenon looks more like a factor of 4 if I look at this graph.
Yeah, and I would have
blue lines.
No, so for helium, I believe it's just a factor of 2. But for xenon, we discussed this in our paper. I think there's a question about the weighting of what different isotopes you had in there, for instance. And when we put that together based on what they're actually projecting to use, plus this factor of 2, this is where the 4 came from. But I wouldn't take that as literal. I would have to go and double check what we said in the paper there. But that's my rough memory of where this is coming from for xenon.
Oh, all right. Yeah, thank you very much.
No, thanks for the questions. Anyway, there's a lot to be said about this plot. I appreciate you asking, but let me put that aside for now. So let me come back to this first part, unless there's other questions, about diving into a density matrix for the dark matter field, from which we might hope to derive this classical wave picture. So the fundamental insight here, in order to crack this question open, is to realize that we are not the first people to wonder about a wave particle transition for a bosonic field. In fact, if you're ever talking about some transition for a bosonic field, odds are there's another case where it's been very well discussed, and that's in the context of electromagnetism. And indeed, there's an entire field that sort of dives into the question of what is the fundamentally quantum mechanical description of the electromagnetic field? And in other words, why is the classical description often a very good one? And this is the field of quantum optics, which was founded by the pioneering papers of Glauber and Sudarshan back in 1963. And so what we're really going to do in the first part of the talk here is just draw on foundational results from quantum optics, port them over to axion dark matter, and we'll find it actually gives the answer to a number of the questions that I raised at the outset. Also, I want to give credit to a very nice paper by Hyungjin Kim and Alessandro Lanocci that came out in 2022. Actually, to my knowledge, they're the first ones that I saw mention that you can use the approach I'm about to tell you to compute some of these variables. I think in our paper, we went beyond what they had there, but they were the first, to my knowledge, to notice this. Okay, so that's where we're pulling this from, but let me tell you what I'm actually going to take from quantum optics. And maybe unsurprisingly, the thing that I'm going to exploit is the coherent state. So this is something that we all probably played around with in some homework homework problems for our undergrad quantum mechanics. And from that, what you will remember is that the coherent state is defined as the eigenstate of the annihilation operator. And so it's some complex, it's this alpha here is some complex number that describes it. And the coherent states have a number of interesting properties, at least in the context of the simple harmonic oscillator. They are states that are sort of the most classical in that the evolution of the position of momentum of the coherent state most closely matches that of the equivalent classical harmonic oscillator. But coherent states actually have a number of other properties that at least I was unaware until I dove into this literature. So one of those properties is that they are overcomplete. That means that you can decompose any vector in your Hilbert space in terms of coherent states, but there is not a unique way of doing this. There are multiple ways of writing it down in terms of coherent states. So another property they have is that they're not orthogonal. So if you take the inner product of 2 different coherent states, you will not get 0. You'll get some overlap between them. So it seems like if you're going to start playing over these objects, those 2 properties might be a bit uncomfortable. However, what Glauber and Sudarshan realized is that these coherent states, these properties, actually allow you to diagonally decompose operators. And in particular, because I want to talk about the density matrix, I'll diagonally decompose the density matrix. And so that's what I've done in the first equation here. I've written the density matrix in terms of some functional P of alpha, or some sort of distribution more accurately. And then it's weighted by this outer product of these two coherent states, integrated over all possible values that alpha could have. So integrated over the complex plane. So this is somewhat remarkable, and it's not straightforward to prove. This is what really one of the key insights in their original papers. And it comes from the fact that these states are overcomplete. As a reminder, if you decompose an operator, say, in Fock states, you would have off-diagonal terms, which are very important to reconstruct the full behavior of the operator. But when you do it with these coherent states, everything is just diagonal. You could wonder whether P of alpha is unique because you don't get a unique decomposition of vectors in the Hilbert space, but actually what was shown by an expression derived explicitly by Mehta in 1967 is that this P of alpha is unique. So what this says is that instead of studying a density matrix, we can study this P of alpha, and this might be an interesting object to consider. So let's think about the properties this P of alpha has. Well, inherited from the properties of the density matrix, because rho is Hermitian, P of alpha must be a real function of this complex variable alpha. Furthermore, because all density matrices must trace to 1, this means that because at least alphas are correctly normalized, alpha contracted with alpha will give you 1, then the integral of P of alpha over all values of alpha will also give you 1. So if you stare at these properties for a moment, you might be seduced into thinking that P of alpha is just a classical probability distribution. But of course, if you think a moment longer, this cannot be correct. It would be shocking if you could write any density matrix as a classical probability distribution, weighting the most classical quantum states, these coherent states. It seems like something would have to go wrong there. And indeed, this was realized certainly very clearly in Glauber's paper. The P of alpha is not a probability distribution. Indeed, you can show that for specific states, P of alpha can take on negative values. So to give you an explicit example of this, if you had a Fock state, the form of P of alpha is what I've given you down at the bottom there, and you can see that this is some nth derivative of the delta function. And some result from distribution theory that I wasn't aware of, but just to let you know, if you have a function that is more singular than the delta function, then it must be negative somewhere in its domain. This is some theorem in distribution theory, and that says that for the Fock states, they are somewhere negative, and so their P of alpha is certainly not a classical probability distribution. Okay, so we can discuss this P of alpha, but it can be a bit of a mess, as this Fock state explicit form shows you. Nevertheless, what Glauber proved in his paper, which is just something that is absolutely remarkable, is that this P of alpha does have enough of the essential ingredients of a probability distribution that it obeys the central limit theorem, a sort of quantum central limit theorem. And to sort of state this in a more rigorous way, what he was able to show is that if you superpose n similar yet independent fields, so statistically independent, then in the limit where the number of those overlapping goes to infinity, the density matrix is described by a P of alpha that is a Gaussian, which is what I'm showing you here. So this is, I mean, somewhat remarkable. I just want to make a couple of comments about what we're seeing here. So just to give you some intuition about what's going on, at least for the quantum optics sort of picture, you can imagine firing many lasers into a single point. And what you want to do is you want to describe the density matrix of the system at the point where all the lasers overlap. And the limit where the number you're firing in goes to infinity, that's where the central limit theorem should hold. Furthermore, just to emphasize, this P of alpha is not, for example, like a pure coherent state. A pure coherent state would have a P of alpha that's a delta function. So this is very much not a pure coherent state. In fact, it's not pure at all. You can actually compute the purity of this density matrix. And what you find by an explicit calculation of this is that it has a non-unity purity, which, as a reminder, if you have unit purity, you have a pure state. If it's less than 1, you have an explicitly mixed state. So this is some explicitly mixed density matrix, which is this Gaussian weighting over the different coherent states here.
So this is not a function in the strict sense, right?
It's a distribution. Yeah, absolutely. I mean,
it could be what is it called? A tempered distribution or something of that kind?
You may be correct. I don't remember off the top of my head, but the example I'm giving you here
Yeah.
of a Fock state shows very explicitly it's not a function.
Yeah.
Yeah, it only makes sense once it's integrated. Yeah. Thanks for the question. But that's certainly not true if the central limit theorem holds. Gaussians are very well-behaved functions, and also it's positive everywhere in their domain. Right? So this will be relevant in a moment. Okay, so that's some basic statements that you could have learned if you just read Glauber's 1963 paper. What are we going to do about this for dark matter? Well, what I'm going to tell you now is that although my goal was to put a lot of this language on firmer footing, I'm again going to wave my hands in the following sense, that it seems extremely plausible that the local dark matter has enough independent random ingredients that this central limit theorem probably holds for the local dark matter distribution. To give you an example, if the dark matter is a thermal distribution, you can actually show that you can rewrite the thermal density matrix in the form of this Gaussian P of alpha. Normally, you normally write the thermal distribution in terms of Fock, in the Fock basis. You don't write it in the coherent state basis. But if you transform it over, you'll find it is also a Gaussian. However, it is not the case that the Gaussian must be thermalized. In this example of all the lasers overlapping, there's no interactions needed. So the system doesn't have to thermalize for it to be driven to this central limit theorem Gaussian. So the picture that I roughly have in mind is that for wave dark matter, we generally don't imagine it had a thermal origin, although maybe it thermalized later in the universe. Nonetheless, where we are locally is not just a random position in the universe. We live in a halo, and halos went through the very violent process of virialization, where all of the dark matter collapsed in to form this sphere that we now live in. And in that process, it seems very plausible to me that you could have had something that was initially not in a Gaussian state, be effectively randomized, come together, and the local dark matter is made up of many different, essentially independent states that when added together will satisfy the central limit theorem. However, I've just given you a whole bunch of words in lieu of an actual rigorous derivation. And so I think it's an open question I would really love to resolve in more detail about what is the exact P of alpha for dark matter. Can we prove it's a Gaussian, or possibly could it be something different from that? As much as I suspect it's probably a Gaussian, to say it would be even more interesting if it wasn't. Imagine if the P of alpha actually kept some information about how dark matter was born, and then maybe we could probe this after we discover dark matter. Of course, that's looking down the line, but I think it would be remarkable if we would be able to say something about the quantum state that dark matter was born in. But unfortunately, I think it's probably likely that with a lot of hard work, you might be able to prove that this P of alpha is in fact Gaussian. So that's the argument as I understand it at the moment. And what I'm going to do going forward is I'm going to assume this Gaussian P of alpha, but I'll make it clear when I'm invoking that and when I'm not. It won't be required for everything I'm going to discuss. Okay, so that's some words about the density matrix, but now I want to move towards actually understanding what would such a density matrix tell me about the field of dark matter itself. So the first step is I need to generalize the discussion so far. I've been talking about coherent states associated with some harmonic oscillator. I need to think about extending the descriptions of the harmonic oscillator to all of the different K modes that we think describe the local dark matter field, or if it's non-relativistic, you can map this K over to a velocity. So that's what I've done here. I've just now imagined that potentially I can make this argument for all of the different K modes of dark matter. And now I need to tell you what this N is, which sets the variance of the Gaussian. Actually, one thing I wanted to mention that I didn't emphasize, that the capital N in the Gaussian is not the same as the N that appears in the central limit theorem. So you can have this Gaussian emerge even when this N is very small or very big, and we'll see why that's interesting later on. What this N, this capital N actually is if you just compute the expectation number of the number of states you have in a mode, that is this NK. So the notation is exactly what you would expect. By this, I mean, if you just compute the expectation value of A dagger A for a given K, which for a density matrix, you just trace that against the operator, you'll exactly find that that's what NK comes out. And so what that then has to be is it has to be the local density of particles at that momentum value divided by the density of states you have for that momentum value. And so we can put this in. The inverse of the density of states is just 2 pi times h bar cubed, because we're using the wave vector and not the wavelength, divided by GS, which is the number of internal degrees of freedom we have, which is different between an axion and, say, a massive dark photon. And then for the density of particles at that momentum mode, well, if we assume that locally the dark matter is homogeneous, we can just put in the local number density. And then for the momentum distribution, it's certainly not homogeneous, but we would assume it obeys something like the standard halo model. But there'll be some wiggle room around that because we're not exactly sure. So that's literally how you compute this NK. But to give you some intuition about what this is, and if I have time to get to the third part of the talk, I'll say some more words about this. This NK is really a measure of how many indistinguishable particles do you have. It's sort of a measure of, because when this number is larger than 1, it means that I have more than one state in a given, essentially in a given quantum state. And there's no additional quantum numbers I can use to distinguish between these states. So that's really the notion of quantum indistinguishability. So when this NK is very large, this is exactly when you would probably expect this classical wave picture to hold, whereas when NK is very small, it's going to be different. And it's related to something called the coherence volume that I'll talk about in the second part of the talk. But technically, you can show that this NK is really what defines when you're going to transition between behaving like a wave and a particle. And just a slightly cute aside that fell out of this calculation that I hadn't appreciated before is that the wave-particle division won't be universal through all wave dark matter candidates. It'll actually depend upon the internal degrees of freedom you have. And so it'll actually be slightly lower in mass for a dark photon because you have more degrees of freedom. So you need more states to populate all of the available quantum states before you start to have this overlapping regime that leads you to what I will now argue can give you a classical wave picture. So I found that, I mean, it's not particularly practical because they're very close together, but I found that somewhat cute.
Nick, those masses, I mean, they're like kind of an order of magnitude larger than this sort of very tildery 1 eV. Is this just because that was too crude an estimate, or is there some kind of additional consideration which is driving this to be slightly higher?
Yeah, I would say good. No, thanks a lot for yeah, that's it. So yeah, exactly. For those of you who have followed, like here in the SNOMAS report recently, sort of defined wave dark matter as much less than 1 eV. So that's where they sort of defined the transition there. But if you go back in the literature, there's all sorts of numbers you can find. And I think sort of the number that I always found most compelling was to think about the number of particles per de Broglie volume. This is what some people had computed previously. And when you do that calculation, I think you get something like 14 eV, assuming a local dark matter density of about 0.4 GeV per centimeter cubed. So it's not that different to the de Broglie wavelength argument. But of course, if you think carefully about it, the de Broglie wavelength argument is a bit nuts because you have a distribution of momenta of particles. So there's no real sense for giving a de Broglie wavelength through a distribution, right? So you have to think about this more carefully. And ultimately what happens is what you're really computing is the number density of particles per coherence volume, not the de Broglie volume. Although it turns out that within order 1 numbers, they're the same.
Can I actually follow up on that question?
Please.
So does this assume a particular form? So because you say that you assume the Gaussian form for every mode, but I mean, I mean, this has a spread, right? The Gaussian has a spread or something, and you're also normalizing
the finite variance, yeah.
Zero mean and finite variance. Okay, I see. But so how much does am I correct in understanding that what you're saying is that the form of the Gaussian, well, or the specifics that go into this actually determine where that boundary is?
So,
or am I completely
no,
off?
no, no. I mean, I'm saying a lot of things here. I'm not always being clear where one assumption is required and the other is not. This NK is, I haven't told you why the classical wave picture comes out yet. So we'll see that in a moment. But this NK will be critical for that, regardless of whether or not P of alpha is a Gaussian. So actually that aspect of this is independent of Gaussian. We'll see why that's important later on. And the interpretation of NK in this form is not going to matter because you can always define NK as the expectation value of the number operator, and it will always have the form that I'm showing.
I see. Okay.
So we'll see that that's actually independent of this. But there is actually more assumption that goes into this specific 18.7 value. I've put in the specific momentum distribution associated with the standard halo model, and I've assumed the local dark matter density is 0.4 GeV per centimeter cubed. You will get variations to these numbers.
Okay, sure. Yeah.
So it's not assumption free at all. Yeah, no, thanks for pressing. Good.
Yeah.
Excellent. But one other thing just to say, further expand on my answer to Kieran's previous question, is that I think part of the spirit of the calculation that we're putting forward here is that this boundary between the two is a little artificial. If you're anywhere near the boundary, you really shouldn't use the classical wave picture because there'll be order 1 corrections to that, as I'll argue in a moment. You should instead use the full quantum calculation. However, I mean, so if you're below 1 eV, you're probably getting into the regime where the classical calculation is very safe. So I don't think I would necessarily, strongly disagree with what was in the SNOMAS report. It is very much behaving like a wave below that. Although if you really want to know where the transition, the order parameter that controls the transition, that is equal to 1 at these values that are given here. But anyway, that's a lot of words to describe this. Good. So some intuition about how to think in detail about this density matrix and what it would look like if it has this Gaussian form. But ultimately, the goal is to try and understand how the behavior of wave dark matter. And so let's focus on the case of a scalar field just for simplicity. And so there, because fundamentally this should be described by some quantum field, I'm going to imagine describing it using the normal canonical expansion in terms of harmonic oscillator for every K mode. Now, of course, normally you would use the continuum normalization. Just to let you know, when you're working with coherent states, the continuum normalization is a nightmare. One can do it, but it's not very straightforward. So ultimately, what you do in the calculation is you put your quantum field in a finite volume and send the volume to infinity at the end. So that's what I'm going to do here. So that's why I've got a sum and not an integral over modes. So then the question is, we're trying to observe this dark matter wave that's described by this quantum field that I've shown at the top. Well, any observable I have will have to have some dependence on this quantum field. But then if I want to evaluate that observable, of course, what I do is I just take the trace of the density matrix with the observable of interest. And so, for example, you could ask about some nth moment of the scalar field that I'm studying. And it's a bit lengthy on this slide here, but you would have an expression of the form I'm showing you. So what I've done is I've taken this phi hat and put it to the nth power. That's what's in the square brackets. And then outside of this, these are the terms that come along for the trace of the density matrix when I expand it using this Glauber-Sudersham P of alpha that I introduced earlier on. So it turns out that actually you can compute this expression even for the quantum field. You don't need to make any assumptions. Actually, Dongyon was the one who understood how to do this using something called the Wigner distribution. Nevertheless, let's think about what happens if we have this nk parameter being very large. So firstly, of course, the challenge if you started to evaluate this expression that you have here is that A, when it acts on the coherent state, will give you alpha, and A dagger, when it acts on the equivalent bra, will give you alpha star, but they don't act on the others. So you'll have to be commuting them through each other in order to get to the outside to evaluate this. And this will introduce all sorts of factors of 1 because famously the commutator of A and A dagger equals 1. However, the generic size of A dagger and A will be about the square root of nk because the expectation value of A dagger A is nk. And so that tells you that if nk is very large, you're only going to make an error of order 1 over nk by ignoring the fact that A and A dagger don't commute. And so that means that for any calculation, as long as n is large enough, you'll make no errors by just replacing A and A dagger everywhere in that previous calculation with the associated coherent state value, alpha and alpha star. And I probably am not going to have time, but at the end, you can do the full calculation without making this assumption, as I will flash later on. So that means if n is very large, then you can replace the quantum field in any calculation of interest with the expression I have at the bottom of the slide here. This phi is the sum over k, and it's got the real part of alpha k to the e to the minus I k dot x. So what determines the alpha values? Well, they're determined by this P of alpha. And just, although it looks seductive, again, that you think this might be just a probability distribution, remember, in general, this can be some horrifically singular object that evaluating the integral can be very it can be quite involved and complicated. If, however, your P of alpha is positive, so this is an additional assumption, it's satisfied by a Gaussian, but not by a Fock state, then this alpha is literally drawn from a classical probability distribution because you now satisfy the various axioms if P of alpha is positive. And so that means that alpha is now just some classical stochastic variable. And that means that phi is literally a classical random field because I've dropped all the operator, which is the quantumness of this. And now if alpha is a classical random variable, phi is a classical random variable. So now we see that there was really 2 ingredients for this thing to behave as a classical wave. We needed n to be large and we needed P of alpha to be positive. And so just to say, if you actually work this through for a single mode, what you will find coming out of this is that literally phi is behaving like cosine mt, which is what we usually assume for the wave dark matter. So in the specific case where P of alpha is a Gaussian, what you find is that phi is a Gaussian random field. It has 0 mean, and it has an RMS value that is controlled by the energy density divided by the mass squared. And if you go back and compute this, this is the same result you would get if you just assume that phi was the square root of 2 times the density, all divided by the mass, cosine mt, and you looked at the same sorts of expectation values. Nevertheless, this has come about in a very different way here, and we really understand what are the statistical fluctuations of the field. In addition, you can compute what are the statistics of the derivatives of the field, and you find that they're actually an independent Gaussian random field because they depend on the imaginary part of these coherent states rather than the real part. So I went into a lot of details here. Let me just step back and tell you what are the key summaries of this first part of the detailed discussion. The first is that there were two ingredients for this classical wave picture to emerge. You needed large occupation and you needed a positive definite P of alpha. Once those are together, that's when you can describe your system as a classical wave. And so if the local dark matter density matrix is described by a Gaussian P of alpha, well, that's definitely positive definite, so you can invoke this classical wave approximation. However, again, I think it would be very interesting to understand, is it possible to actually probe this P of alpha with an experiment? It's not completely straightforward because you're trying to understand the quantum fluctuations of your dark matter system, but every detector we construct is quantum mechanical itself. So you need to look for them behind the quantum mechanical fluctuations of a detector. So this is something I'm thinking about in detail at the moment, for example. Okay, with that, I think that's probably one of the main parts of the talk. So just to pause in case there's any questions, I'll say a few words about coherence, and then I would just wave my hands furiously about the third part because I'm not going to have time for that.
Yeah, I was just going to ask you a bit, as well as getting like the RMS value for the field, you also mentioned you recover the statistics of it. Does this Rayleigh distribution pop out as well from this picture?
Good. There's a lot I could, yeah. Yes, okay. Just to say what happens here, why does this happen? Effectively, so maybe for others as well, I mean, Kieran and I have both thought about this exact question. Often what happens when you're taking experimental measurements of the axion field is you measure some time series, take the Fourier transform, and then compute the power spectral density of the field. And a question that people had is, what is the statistical fluctuations of the power spectral density? And there'd been some heuristic arguments that it should be exponentially distributed. It turns out that this formalism predicts the same thing. And the reason for that is that if you have effectively the power spectral density is sensitive to the real part of the field squared plus the imaginary part of the field squared. If you add the two independent Gaussian squareds, you can show that's the exponential distribution. So it actually comes out like literally immediately from this, very quickly, but for a very different reason, I think, to some of the earlier heuristic arguments. Good. So let me now say a few words about coherence and how you can understand this really fundamental property that often plays a large role in determining the experimental detectability of wave dark matter. So in the first part of the talk, what we were focusing on was correlators or equal time and position correlators of the dark matter field. The next natural thing to explore is unequal time and position correlators. And if we assume, as we usually do, that the dark matter is stationary and homogeneous, when we're looking at, say, the two-point correlator, all that is sensitive to is the separation in time and the separation in distance. And so what we can define this as is some autocorrelation function of those separations. That's what this gamma is. And intuitively, what this autocorrelation function measures is if I know the field at a given time and position, how much information do I have about the field at some other space-time position? Intuitively, you might imagine that your information would decay as you wait longer and move further away. However, if the field is sufficiently simple, let's say it's literally just a cosine, well, I probably could track the evolution of that system forever, and so I shouldn't lose information as I move further apart. It turns out that with very minimal assumptions, you can actually derive the exact form of what this correlation function should be. If you just work at the case where you just look in time, you turn the distance to 0. You can keep the distance in here. I'm just dropping that for simplicity. And it turns out that this correlation function is controlled fundamentally by the energy distribution of the system. That's this P of omega. That is the probability distribution for how energy is spread between the different modes of this field, for instance. So this is a slightly, abstract formula if you haven't thought about it before, but we'll dive into this in a moment. And so in order to get some intuition for how this behaves, let's focus on the specific case of dark matter, where the energy is famously the mass plus a half mv squared, because it's non-relativistic. And then to get explicit forms, let's just assume a specific form for the speed distribution and therefore the energy distribution. And I'll take this conventional standard halo model, which has the form I'm showing you at the bottom here. It has a mean value that's controlled by the fact that the Earth is moving through the dark matter halo. That's this VO dot. And then there's some spread to the distribution, which is this V naught. Okay, it turns out you can actually compute the gamma function, this autocorrelation function analytically for the standard halo model. And this, if I just plot the result, this is what you get here. I've artificially enlarged the speeds in the standard halo model. And the reason I do this is because there's essentially two different scales. There's the natural oscillation scale you can see, and then there's this decay scale here. If I use the real values, the oscillation scale would be much, much shorter than the decay scale, so it would be hard to see them. So I've just enlarged it so that you can see, but the basic idea will carry over. And really what the core point I want to draw to your attention here is that you can see that indeed for the standard halo model, this correlation function is decaying as you wait longer and longer in time. And effectively, although it's not exactly, there's roughly an exponential decay time to the information that you have as you wait longer from your first measurement of the field. And this exponential decay time really is, in a more rigorous sense than what I had before I dove into this, a measure of the correlation time of the field. So this is something that I'm sure a number of people in the field understood, but I don't think it had been widely appreciated, is that this is really how you should think about this correlation time. And indeed, if you go to the field of quantum optics, there's a literal definition you can give to the coherence time in terms of this autocorrelation function that I defined previously. So this is where I really can put an equals in here. And just to tell you what's going on, if I just took some simple ansatz where the correlation function was an oscillating cosine with some exponential decay, indeed the scale of that exponential decay does come out of this definition as the correlation time. So this intuition I gave you on the previous slide does marry up with this definition. But more to the point, what happens if we start talking about dark matter? For dark matter, we have famously a non-relativistic velocity, so you can substitute in this for a generic form of the speed distribution, and you can actually compute exactly up to corrections in V what the correlation time is. And it has the form that I'm showing you in the middle of the slide here. And at least for me, this was a real eureka moment when this came out, because it explained immediately why in earlier calculations, people kept finding that the sensitivities depended upon this odd integral of the speed distribution. And the reason is because that is literally the correlation time, what comes out of the correlation time for a non-relativistic field. And so because the correlation time controls fundamentally the sensitivity of many experiments to wave dark matter, it's not shocking that this integral came out because it's what controls the correlation time itself. So this answered one of the surprises that I'd had about this field. Coming back to an explicit form for the standard halo model, you can actually compute all of this to any order and velocity you actually care about, and it has the form that I'm showing you here. And just to tell you, again, this resolves some questions that I had. If you remember earlier on, I was very bothered by the fact that if you took the correlation time, naively it seemed that if you put a detector at rest in the halo frame, the correlation time would diverge. But if you stare at the prefactor of this expression here, just to let you know some a relation you can confirm in Mathematica, if you take the error function of small argument, it has a linear scaling. And so that means if I send VO dot to 0, the Earth's velocity, actually VO dot will cancel out and I'll still have a finite correlation time. If, however, I send the width of the distribution to 0, the correlation time diverges. And this is actually physical, because if I send the width of the distribution to 0, that means that every single mode in the field has the same energy. And that means I can literally treat the field as a cosine of that energy times t. And if I measure it at one time, I know how to track a cosine, I can track it forever. So the correlation function never dies off, so the decay time diverges. In terms of the actual expression that I've given you here, the corrections I've put in parentheses are completely irrelevant. They're of order 10 to the minus 6. But this is just to emphasize that this is a literally well-defined quantity, and I can compute it to any order of accuracy I care about. And it turns out for the specific form we have here, the correlation time is about 3 milliseconds, which is within a factor of 2 or 3 of what the tilde definitions had given previously. So let me just say briefly, because I can see I'm already running out of time, that you can push all of these ideas almost immediately to the frequency domain, which is at least often how I think about wave dark matter. And it turns out, again, a detail probably some of you were familiar with, but I wasn't, is that the power spectral density, this measure of how much power you have in your field at a given frequency, is literally the Fourier transform of the autocorrelation function. Although it's a little bit technical, this is why there's a theorem named after it. And there's also some business about this half factor at the start that I could talk a lot about, but let me not unless somebody's interested. So because of this definition, you can actually immediately compute what the power spectral density should be for a generic scalar field, and this is what the expression you get here, and it just comes out immediately. It actually agrees with some previous estimates there had been for what this power spectral density should be, but that came out of a really heuristic argument. So it's very nice to see that justified. And further in the frequency domain, you can understand that this power spectral density has a width that is controlled by the correlation function. The longer the correlation function, the narrower the width of the field. So there is an exact mapping between the intuition that people often have in the frequency domain and this definition of the correlation function that people are using in quantum optics, for example. Just a flash, you can repeat this same calculation for position, where you set the time separation to 0 and just study how your correlations evolve as you move in position. Of course, initially this might seem more complicated because position is a 3D variable as opposed to the 1D time, but actually in practice this is a much easier calculation because in the non-relativistic limit, you get a linear dependence in the momentum, whereas the correction that you have to time comes in quadratically because of a half mv squared. So one can compute this, you can study these objects here, and there's some analog of the coherence time, which is called the coherence volume, because realistically, in principle, if you thought about coherence lengths, you could have a different one in each direction you look. And it turns out you can give this you can compute this exactly again for the standard halo model, and you find that the scale of the coherences are around 700 meters for a dark matter mass at around a micro eV, and you can scale this to whatever other value of the mass you may wish. Furthermore, I told you earlier on that you can compute this NK that I gave you once you know a form of the coherence volume. And indeed, this is, I think there was a question about this, about what assumptions went into this. I was assuming that it had the standard halo model form so that I could do the calculation that I'm showing you at the bottom. And so, for example, you can compute what the occupation number is for like where ADMX is searching. And indeed, you can compute it. It's very large. It's about 10 to the 29. And so you really can, for all of your calculations, assume that ANA data commute because you're only going to make a 10 to the minus 29 error in doing so, for example. There are higher order correlations one can compute. I flashed this because some in quantum optics, this G1 and G2 are very interesting. They're related to field correlations, intensity correlations, and the Hanbury-Brown twist phenomena that some of you will have heard about. But this is just to say that any correlator you might care about for wave dark matter, once you have this formalism, there's no obstruction to computing this. You can just sit down and determine them. So to step back, the main summary of this is that this coherence quantity that really plays an important role in the discoverability of dark matter absolutely has a rigorous definition and a long history in the field of quantum optics. It's a measure of essentially the exponential decay time exponential decay in time or distance as you move away from some measurement of the field. And you can give it an exact equality definition that matches up with a lot of the heuristics we have, but satisfies various properties that you would want of this concept. So unfortunately, there's been questions, but this is mostly due to my own time management. I haven't left enough time to cover this wave particle boundary section. But let me just flash to the conclusion here. What essentially you find is that you can do full calculations through the wave particle boundary. So you just go back to this original calculation I was talking about for the dark matter field operator, and you just never assume that ANA dagger don't commute. You keep track of the fact that they commute and work through this. And what you can find is that for various observables in the large occupation number limit, they behave as you might expect a wave to behave, whereas in the low occupation number limit, they exactly behave as a particle would, but somewhere in between, you get completely different statistical properties of the field. And it's just something you can explicitly compute. There's a lot of interesting aspects to this, and I'd be happy to discuss this if people are interested, but for time, let me not go into the details here. Good, so stepping back a bit more, I think broadly, there's so much excitement and effort, I think justifiably, for the search for wave dark matter. The least we can do as a theory community is to make sure we really understand what we're talking about here. And I think for this, we really draw a lot on the pioneering work done by Glauber and Sudarshan and others in quantum optics to understand exactly how we should rigorously think about the wave. But although I've told you some steps forward in terms of our understanding, I think a lot remains. For example, ultimately, I did wave my hands when I was telling you about exactly what this P of alpha is. And I think it would be very interesting to understand, is it really in this Gaussian form? Because if it isn't, that would open the amazing possibility you could actually probe experimentally the quantum state dark matter was born in. Furthermore, though, if you're going to do this, you're going to need to understand how can you measure the statistical fluctuations of dark matter behind the fluctuations of your detector itself. So this really mandates an interface with quantum measurement theory. And further, let me just end with a slightly provocative statement. A question of is it even possible to think about extending any of this business to fermions? And the reason I mention this is because there actually was some papers by Glauber and Cahill in the 1990s thinking about how to extend the formalism I've just told you about to the fermionic case. Of course, you have to change things from essentially step one, because I was talking about coherent states, which are a fundamentally bosonic object. Although there is a fermionic analog of the coherent state, but the question of how much of what I've just told you about could be pushed over to, say, fermionic dark matter or fermionic states more generally is something I'd like to understand. Okay, with that, thanks for your attention. I apologize for going over time, but I'm happy to hang around if there's questions.
Great, thank you very much. Yeah, questions?
Yeah, I wanted to ask one
Bruce?
question.
Yeah, well, you're going and then I'll go to Bruce. Yeah, go ahead.
Okay. Well, thanks for the talk. Like, first of all, I wanted to ask, I have seen for example, in an experiment called Quack's proposal, they are considering coherence times difference, like for the gradient, so to speak. So basically, if you are measuring gradients, like the coherence time would be different to having like fields. So I guess that's related in some sense to the what you said about the correlator, right? Like if you calculate the correlator for the gradient, you might get a different coherence time, right?
That's not, yeah. So the coherence length is different to the coherence time, 100%. But if you're computing, I think that the basic physics will probably be very similar. Now, I haven't computed what the appropriate object would be if you started taking the gradient of this field, but I would be surprised if it was anything more than like factors of 2 or 3. I think again, it's going to come out to be 1 over mv squared, where exactly what v is, well, they're all about the same for the standard halo model. So yeah, I mean, it might be worth just double checking this, but I suspect the coherence time will be very, very similar. But maybe just to say another thing about this formalism is that there's really no obstruction to just doing computations in the time domain. I think it was always very unclear to me about exactly how should you think about the axion evolution in the time domain, but I think this picture makes it completely straightforward. You know exactly statistically how this thing is evolving. You know how to compute any quantity you might be interested in. So if they are worried about exactly how their system is evolving in time, then you would compute this. But broadly, when I've looked into this, I found that people knew what they were doing. They got the parametrics right. You just might change something by a factor of 2 or 3.
Yeah. Like as far as I remember, it was like 0.5 the coherence time for the field, so to speak. So there was not much a change.
And I think if I said correctly, it was like a millisecond for a micro EV, and I think Quacks is like a milli EV, so it would be around a second. Yeah. So that sounds about right.
Bruce.
So my question is, can you spend 2 minutes talking about the transition regime? Because I flatter myself that I understand what a particle limit and a wave limit look like, but I imagine the transition is non-trivial. So tell me about it.
Yeah, good. Thank you for asking me that, for bailing me out of my poor time management. So what you do here, let me tell you about one example of one calculation you can do. And there's a lot of technicalities that you can address, but let me just brush through them quickly. Here's a simple question you can ask. How much energy is in a box, okay, of dark matter? Now, you know what the answer to that is. It's the local dark matter density times the volume, okay? It's not that interesting. But what is interesting is what is the fluctuations in this? Because if it's a particle, the fluctuations better be Poisson, because it's how many particles do I have in the box. If it's a wave, it's probably going to be different. People had argued in the literature that due to constructive and destructive interference, probably actually the fluctuations will be exponential. But if you stare at the Poisson distribution and the exponential distribution, there is no limit that they tend to each other. So this had bothered me for a while, like how could I actually smoothly transition between these two? And what turns out to be the case is if you do the full calculation, there's some other distribution that does tend to the Poisson and the exponential in some limit. At least, and this is just one calculation we've done. I suspect there are other observables you could compute through the boundary. So when we go through this calculation, just to show, like you can do this for the full distribution, but you find that the mean has some value n. N is again this literal the occupation number, whereas the variance is given by n 1 plus n. So in the Poisson, in the particle regime, n is very small, and so the 1 dominates, and so you find that the variance is equal to the mean. That's the Poisson distribution. However, when n is very large, the variance goes to n squared, and you have variance equal to mean squared, and that's what you get for the exponential distribution. And what you find in between, though, is you can see what I'm plotting in the middle. When n equals 1, the blue is the exponential, the orange is Poisson, and the actual distribution for a Gaussian is something completely different. You know, it's in the ballpark, but it's just a different statistical distribution. Yeah.
So can I follow up? Oh, sorry, there's another question.
Yeah, we can go back. So maybe let's let Roland ask, and then we can go back. Yeah, Roland, go ahead.
Thanks, Nick. So on this question of the Gaussianity or not of P alpha,
yeah.
So this is something that you were flagging that you could actually potentially measure. Is that right?
In principle, you can. I mean, there are protocols. There's a whole literature on this of reconstructing the density matrix of some system by what measurements you can do to get at this. I don't claim to understand that full literature, but I can tell you the following is true. If you have a Gaussian distribution, the variances of various observables will be very different to if you just had a pure coherent state. And so then, but generically, all of the information is held in the fluctuations. You always get the same mean value, usually, but the fluctuations encode exactly what quantum state this system is in. So what you would need to do is you would need to start doing a detailed measurement of this field and mapping out its various correlators. And from this, you could in principle try and reconstruct P of alpha. But then there's this massive complication that on top of that, your detector's fluctuating. And really disentangling these two is the domain of quantum measurement theory. And at the moment, I'm trying to understand, is it plausible, or what would it take if you made a measurement of dark matter to measure the P of alpha? In some sense, but maybe I'll give you.
Okay, well, sorry. I mean, that was that opens up to my actual question, which was, say you're running a cosmological simulation, which includes dark matter. Is that going to be in any way dependent on this Gaussianity or not?
Yeah. Again, so I don't know the answer to that question in all generality, and I would like to. My broad statement is the following. Again, the mean behavior is always about the same. So broadly, the properties you'll get will probably be very similar. But if some observable you have is sensitive to the variance, then you might get some deviation from this. And this was one thing I was going to flag at the end here. It seems that if you look at a question you could ask is, let's say I study the fluctuations of dark matter over galactic scales, like kiloparsecs. So of course, famously for fuzzy dark matter, you can get amazing deviations from WIMP predictions at those scales. But if dark matter has a micro EV in mass, where it has a correlation length of a kilometer, you probably don't expect much, any remnant of that at a kiloparsec. At least that was my expectation. But that's just not correct, actually. It turns out if you compute the variance in the fluctuations over kiloparsec scales, the variance is enhanced beyond the Poisson distribution by a factor of n, which, again, is 10 to the 21. Now, does that do anything? I'm not sure. I would like to understand if there's any potential observable that is sensitive to a much larger than Poisson variance. But for example, in body simulations, the variance is by definition Poisson because they use particles of a given mass, right? So if there's some observable that is potentially sensitive to a large deviation of the variance from Poisson, this would matter. I have some ideas, but I haven't checked them yet. I have to admit, this is something we only realized right at the end of the paper. So in principle, there's a deviation. Does it matter for anything? I don't know yet. Maybe.
Okay, that seems super interesting. Yeah, thank you.
Oh, thanks, Roland. Yeah, it's a very interesting question.
Dipan, did you want to go now?
Yeah, so can I go back to that, maybe ask a follow-up question to what Bruce just talked about the wave. So it's, I mean, so when you talk about the boundary, let's say, I mean, it's also a measurement question, right? I mean, it's not just whether, like from a theoretical understanding, whether there's a sharp boundary between what I call a wave or particle. When I measure something in a lab, right? I mean, the instrument itself intrinsically has, well, most instruments are classical, and then I can devise maybe some instruments which have a quantum nature. So what I measure, I mean, if I could measure one point on that graph, it's one thing. But if I'm merely dealing at the boundary, it's also dependent on how the instrument reacts to that. I mean, whether I can make a statement that what I'm measuring is really a particle or a wave or something of that kind. I mean, is that a weird question to ask?
I mean, I guess I think about it differently, right? Like fundamentally, everything's quantum, not the other way around.
Sure, everything is quantum fundamentally. That I agree, but that's fine. Yeah, absolutely.
And really what turns out to be the challenge, and the community is grappling with this more broadly, is that if this system only couples to you very, very weakly, you have to push every background down until usually you're at or trying to get below the standard quantum limit. So often from the perspective of wave dark matter, you're almost always starting to think about this detector is behaving quantum mechanically. So that's the thing I would say to the
I
first
see. Okay.
The second thing I would say is that these it could well be that there's some measurements that, yeah, I mean, there are certainly measurements that will change what the outcome is in terms of the statistical fluctuations. Like if I'm asking how much energy is in a box or volume, it fundamentally depends on the size of the box. I can tell you if you make the box small enough, you can prove that the statistics will always collapse back to Poisson. But yeah, so there is, it does,
Sure.
in some senses, it depends upon, and so then it's a question of like, what area are you sensitive to?
I see. Okay.
For a given detector, I think generally, but even though it depends on what you're looking at, this N that enters is just a fundamental property of the local dark matter. So that doesn't, that only depends on the local energy density and the local speed distribution. So that N, which controls the statistics, like the exact variables depend upon the specific observable you're looking at, but often they will depend on N, and they can depend on N differently, but that N's always the same. At least if I'm looking at...
Right, okay.
So some aspects change, some aspects don't, is my hedged answer to your question. Yeah.
All right, yeah, sure.
Bruce?
So I'm going to ask another follow-up question to something that you raised in the talk, and that is to the history. So you said it's plausible that from the violence of the initial composition of the galaxy via accretion, that all of this has effectively become randomized. And okay, on a hand-waving level, I agree that's plausible. But you're not talking about tiny little balls, you're talking about quantum mechanical objects, and the history is non-trivial. And the whole point of this discussion is that it's not just a matter of N being large. Because as you correctly observe, if you take N quantum mechanical objects completely coherent with each other and overlay them on each other, you haven't made a classical wave. You've just made a very, very big quantum state which doesn't have anything like classical properties. And so...
just to interject on one point here, the N, I mean, this N that defines...
There's more than one N, I understand.
Yeah. But you can have this thing driven to the central limit theorem with very low N, like very low...
but what's doing that?
What is doing that is that this thing still has enough of the essential ingredients of a probability distribution that as you add many of them together, the higher order moments are all suppressed in the same way as the classical proof of the central limit theorem goes through. Like this P of alpha, you can still think about it in terms of moments, even though it's not a classical probability distribution. And as you start adding many of these things together, the higher moments become less and less relevant. So
but it's the similar yet independent that's doing that. I mean, it doesn't work with strictly identical things. That's the point.
Well, it's yeah, okay. Literally identical, no, but if they're statistically independent, then yes, yeah. So if it's like, for example, I could produce a coherent state, and I can't then think about breaking the coherent state into different things and making the argument it's driven to the central limit theorem. I need independent coherent states to come together in order to make that argument go through.
Right. So tell me about that's fine.
Yeah.
Tell me about the detail of what you're having to assume in the hand-waving argument that says, composition by accretion will just do this.
I think so. The picture I have in the back of my mind when we're thinking about virialization is you compute there's some small overdensity, it grows and it grows and it grows until it leaves the Hubble flow. But then what happens is, in the normal spherical collapse, it all collapses down to a point and goes through each other. Of course, that's not the case. There'll be some finite angular momentum that means these things move past each other. But if this thing was all one big coherent thing initially, this set of gravitational interactions it will have as it goes through, I would think would start to statistically randomize it. But I'm waving my hands even as I'm saying this. So how exactly?
And I noticed that during the talk. So I'm just
right. I'm trying to be very honest about this. Yeah. I mean, maybe very extremely vaguely, in cases where you have a complicated system, the central limit theorem applies in a shocking number of occasions. So the fact that there is some quantum central limit theorem, and we know that dark matter went through some very complicated process, tells me that this probably applies, but I haven't proven it. And I can tell you I wanted to prove it, but as you probably are familiar, the domain of evolving density matrices goes into this question of master equations, and it's very complicated. I haven't been able to get a hook yet to understand how to rigorously prove this, but it's something I'm thinking about. Yeah.
I mean, and the other thing is, I mean, effectively collisionless objects don't behave the same way as objects that have got dissipation. And so some of our classical intuitions about these things are not helpful.
Sure. Yeah. And to say, just to maybe add to the case where it might not be, I mean, dark matter interacts very weakly. So
Yeah.
if you hope anything would not, essentially, this is like some process of decoherence. If you would expect that the thing wouldn't decohere, a very weakly interacting state is exactly what you'd want. And even again, it's my dream that this doesn't get driven to a Gaussian, because that would then mean that a discovery of dark matter, we could then probe the way it was born by measuring its quantum state. But unfortunately, I think that's very unlikely, but I haven't proven it yet.
Okay, thank you.
No, thanks for the questions. Appreciate it.
Okay. Well, yeah, people should feel free to go if they want. But I did have sort of final question about well, maybe a couple of questions, but so the coherence volume formula you showed, this also looked like it had just a V0 in it, but I assume this is also some complicated combination of V0, V O dot, and the various parameters that show up.
Shockingly, a great question. Yeah, I was shocked by this, but for the standard Halo model, it doesn't. So it turns out that the integral, when you substitute this in, is simple enough that you can just shift the domain you're integrating over and completely remove, where did I put this silly thing? You can just shift the VO dot away. Because you start out in this form here, it's just gone. So in principle, it could have shown up, but in this case, it isn't there. But to say actually for a generic momentum distribution, you'll have, like, you could have something that has different widths and momentum in the 3 different directions, and that will have 3 different coherence lengths. It will have a different coherence length based on that width. So in general, this doesn't happen, but it just turns out for the simple Gaussian form, it cancels out. Now, again, it's because this silly thing that the time comes in as v squared, that you're not able to do the same change of variables, and it's a different integral. You can't do the same change of variables to get rid of VO dot from the coherence time, but it literally vanishes from the coherence volume, which I was not expecting, and it does go away. So it's not this approximation; it does go away.
Yeah, it's interesting. I'll have to look into that. So this coherence volume doesn't annually modulate, then would be one takeaway from this.
No, yeah. But anyway, there's more things, like we talk about some details in the paper here. Like, what do you mean by this? Like, what happens as you start looking at larger and larger dark matter, lower and lower masses, so larger and larger coherence volumes? At some point, I mean, the coherence volume will encompass the sun. And then, I mean, things have to be changing at some level. And essentially what's baked into this is some assumption about isotropy and homogeneity. And those assumptions will be breaking down once you start getting to that regime. And I think it could be a bit of fun. I mean, that's not maybe my favorite mass range for dark matter, but I think at least the physics could be very interesting. So it could be interesting to think about that. But yeah, the reason we don't see this is because we've, by fiat, assumed it's homogeneous and isotropic.
Yeah. And the other thing was, so I guess, so I know you sort of made very clear what your motivation was at the beginning. And I assume that, so this issue to do with the sort of tilde level relations, I don't think experimentalists need to have to worry so much, because I don't think they're using those necessarily all the time. I mean, theorists use them to make estimates and stuff, but experimentalists, they care about the line shape, the stochasticity of the field, which I think you're basically saying it's just the same. Do you think there are any cases apart from this sort of these Casper projections you made at the beginning? Do you think there are any cases where there may be revisions needed to do this properly, perhaps in like the sort of terahertz regime where you're going to be closest to the wave particle boundary?
Yeah, not good. So here are some things. Yes, naively, yes, but then you really start to get into this business about how do you disentangle this from the quantum mechanics of the detector. So naively, let me tell you a case I might worry about, and that would be as I move up to higher and higher masses, Oh, sorry. As I start to, okay, it is higher masses, but actually it's lower masses for the argument I'm about to make. You'll be aware that there are various proposals to detect quanta from milli-eV dark matter, right? There are these like various ideas to detect, a number of these being excited. But when they do this, they always envision that what's happening is you've got boson fluctuations because you're doing some counting experiment. But the fluctuations in the dark matter will be violently non-Poissonian because n will be enormous, even at a milli-eV. So naively, you would think that they're getting their statistics completely wrong, and it could change like what their 95% limits are by a large amount. Except that then the quantum mechanics of the detector is critical to disentangle that. And actually, I think could change some of these statements. So that's one case where I mean, this is a reason I'm thinking about this. It could change like what are the measurement statistics of some of these counting experiments at high wave masses, low particle masses. Another case, I would like to understand this in a bit more. Like people are talking about doing single quadrature measurements, for example, right? And I told you that essentially what turns out is that each quadrature behaves like a Gaussian field. So if you just measure one quadrature, you won't get exponential fluctuations. You'll get chi-squared with 1 degree of freedom fluctuations. So people have talked about doing exponential fluctuations, I think in that case there, but there it will be slightly different. This again will not change the results by orders of magnitude, but I think in detail these things matter, right? As we push down towards exact things. But no, I think broadly the intuition I have is that the order of magnitude sensitivity is set by the means of everything. And the mean you could tilde correctly, basically. Actually, one more case that I think is important to understand a bit more is I think that everyone has a good sense for how to measure the axion signal in the frequency domain, okay? But I think in the time domain, it's a bit less clear, right? I think how exactly these coherence properties were mapped on this was never super clear to me. And it could be very nice to understand how to do a rigorous time domain analysis of the axion field. For example, if you're looking for something like a transient signal, of course, you can do this by chunking your data in the frequency domain, but just having a fundamentally time domain analysis of this would be very useful, I think. So that's something I'm thinking about with Josh at the moment, for instance. But
are there examples of kind of realistic experiments where you would have high enough signal to noise to get away with doing stuff in the time domain?
But the definition of the Fourier transform is a completely invertible map. So there should be nothing you can do in the frequency domain you can't do in the time domain. But I just never understood how to think about the wave clearly enough that I would even understand how to construct the question of what am I doing in the time domain. So yeah, it should be you should be able to do everything in the time domain you can do in the frequency domain. But because it's one-to-one, the frequency should capture everything. But I still think conceptually, and especially if you wanted to look for transients, it would be very nice to know how to do this in the time domain. But yeah, broadly, I don't think orders of magnitude changes. It's generally order one things. But yeah, if $100 million project, I want to get the order one things right too.
Yeah. All right. Last chance for anyone to ask questions. If not, we can